copy the link and put it in the chat so that you guys can keep that link in advance as a means of revising or something. So let's continue. Now, as we continue here, we are looking at, an inductor. That's what we are looking at. We are now looking at, we're looking at the inductor. Now, we are saying that an inductor is an energy storage device. Now, during the week, I posted something in the group where I was trying to comparison between a capacitor and an inductor, but not that. I also tried to show in another post how these could be used. So this inductor is an energy storage device. I don't like that. What are we doing here? Sorry, guys, I don't know what's happening. Let me just ensure that this. Did we press again? Then we'll go here, open this guy once more. Then go here. So recent opens. We're still opening in the same style, huh? Really? The software also. All right. I think this thing doesn't just want to work. Okay, we can work with something new. Yeah, so we can proceed. So we are looking at inductors. So we define this to say that it's an energy device. It's an electric energy in form of electric field that. So an inductor might be like that. So this inductor represented by L in henries. Okay? It's measured in henries. So given an inductor like this, you've got 12 volts input, and this 12 volts goes through an inductor. Okay. Then you may have a resistor in this very circuit like that. Then your circuit might continue. And then you may have something that we may call a load, okay, or something that you are powering. We discussed this last time. Now, if you have a circuit like this, the purpose of this inductor that you have here, purpose of your inductor is to store electric energy in form of electric field. So around this coil, you are going to form an electric field around it. Now that particular electric field that will be formed around this particular coil like that would represent a storage of energy. Now, an inductor allows the flow of DC. It blocks DC and it allows the. So, given that the current that's flowing here is DC, it resists the flow of AC. Okay. Then inductors are used in transformers. So when you see a transformer, what is in there basically is an inductor. Inductors are used in chokes. So when you see these fluorescent tube bulbs that you see, what happens there is that a fluorescent tube will have an inductor in it. Now that inductor will call it as a choke. Now what's going to happen is that when power from the mains flows through this inductor, it will start charging up until this magnetic field grows. Now when this magnetic field grows, it will keep growing. But at the moment when it collapses, it produces a high voltage. Now that high voltage when it collapses makes the fluorescent bulb to go on like that. That's how we use that. Now, it's also used as a noise filter. Also used as a noise filter. Okay? It's also used in oscillators. It's also used in oscillators. So the inductor is also used in oscillators. It's also used as a noise filter. It's used as chokes. It's also used as a transformer. So these applications, you meet them a lot in your design. For instance, if you're designing a power supply or something that would be providing power. So if you look at the way we have done in the circuit, this particular circuit here, this could be our power supply here, PSU power supply there. So this circuit here will be for a power supply. So when you design this, so that you're able to provide power on the load side, this side. So you find that inductors usually are found in the power supply circuits as well. Now, you notice also that in some chargers, either phone chargers, computers, or just power supplies, you find that there's a bead. So you find the cable might be coming like that, then it has a bead like that, and then this cable continues. Now, this bead here is called a ferrite bead. Ferrite bead. Okay. Now, what this ferrite bead will do? In essence, a ferrite bead is basically just an inductor. That's what it is. Okay. It's basically an inductor. Now, what this will be doing is equivalent to what you have said here. It's for noise filtering. So when you are charging your phone and all that, that current that is disturbance, that is not, which has ripples in it, or it is, kind of oscillating, or it has transients in it. So DC current, we expect it to be straight like that. But you find that sometimes it might look like that. So this might not be clean. In fact, even what I've drawn here, this is also not clean. Okay? A proper DC must be flat with no issues like that. Now, if this is what you are going to use, what's going to happen is that your phone will probably not be able to charge properly because of these transients like that. It will even start heating. So nice chargers, actually, if you are going to buy a charger, always buy a charger that has some kind of ferrite bead, because it prolongs your battery life, it prolongs your electronics in your phone, the life of your electronics in the phone, like that. That's how this works. So when the flow of current is coming from the charger like that towards your phone, this ferrite bead will ensure that those high spikes like these will be cut off, will not pass through. We said that an inductor resists the flow of AC. How does AC looks like? It looks like that. Okay, that's how AC looks like that. How does DC looks like? DC looks like that, straight. Okay, so DC looks straight like that. So that will be your DC. Now, what you're saying here is that this inductor allows the flow of DC and it resists the flow of AC like that. Now, because this AC has those ripples, that's why it is restricted in terms of its flow. So what's going to happen is that this example I've given here, when your DC supply is you're charging your phone this side, okay, this ferrite is going to clear out because it resists the flow of AC, those ripple signal to be cleared nicely like that. That's how inductor, a special inductor we call ferrite bead, actually cleans or filters the signal in that particular sense. The other popular component that you'd find is something called a diode. Now, this particular diode, if you have a circuit like this, let's say this is 5 volts, then you have diode in your circuit like that, then it goes, and then let's say here you have got something called ARA, which is basically the load that you're powering, like that. This load can be anything. It could be an Arduino, it could be an LED, it could be a light bulb, or anything. That's a resistive load there. Now we have got this diode here. So let's call this diode E1. Now this is 5 volts, positive, negative. Now this diode has got characteristics. Okay. One of the characteristics of this diode is that it has the material from which it is made. So if this diode is made from a silicon material, it's going to experience a 0.7 volts drop. What that means is that the threshold, okay, in order for current to start flowing through here, is that 0.7. So when you turn on, before this comes to 5 volts, this won't go on. Not until this becomes exceeds this 0.7 volts. That's when now the power will start, or the signal start flowing through. So what that means is that we have a 0.7 voltage drop at that particular point. So basically what the voltage that we expect to reach this side would be a 4.3 volts, like that. Okay. Now, these particular diodes have got wide applications in electronics. Okay. Diodes have got wide application in electronics. Some of those applications is depending with the type of diodes, because these diodes have types. If you are working with, say, a Schottky diode, you could be able to use these diodes as a discharge. So let's say you are driving a motor. Okay, you have a motor. Now this motor comes to stop. This motor was rotating like that. Then the motor comes to a stop. So when the motor stops, it's a mechanical device. A motor is a mechanical device or an electromechanical device. So when it comes to stop, it has some energy. Where does that energy go? If you're designing a circuit that will be driving a motor, you should be able to anticipate where you're supposed to take that energy when it comes to a stop. Okay? Now, such a diode might be called as a free wheel diode. Okay? You can use example Schottky diodes for that application. Now, what's going to happen is that you're going to pair diodes, maybe let's say 2 of them or 4 of them, like that. So you'll have, that's your diode there, then you'll have another diode there, then you'll have another diode there, then you'll have another diode there, like that. Now, what's going to happen here with these 4 diodes is that when this motor comes to a stop, remember, there is that bit of accumulative power or residue power that will remain in it, in form of whether voltage or whatever that is. These diodes will take that power. Now, remember, the diode is able to consume 0.7 volts. So if we pair 4 of them in the same place, meaning this one is taking if they are in parallel like that, this is going to take 0.7 volts, this one 0.7 volts, that one 0.7 volts. So basically, we have 1.4 volts, about 2.8 volts, 2.8 volts, like that. So 2.8 volts that might be available as soon as this motor comes to a stop, can be consumed by these diodes without making the circuit hot. If we replace that with resistors, the circuit might be quite hot like that. But then the material from which these diodes are made, they will consume 0.7 volts with less or no problem in that particular manner. So you'd be able to use that diode for that. If you have ever bought something called a motor drive, for those who went to university, and then you were working on some projects and things like that, you'd realize that you bought some motor drivers at some point. Why didn't you just drive that with maybe using a transistor and things like that? Let me just call you back in the next 20 minutes. Let me call you back in 20 minutes. Yes. So you did not drive it just using transistors alone, because when that motor comes to a stop, you need to be able to dissipate the energy that it came to stop with, that residue energy. So there, if you buy a motor driver, you look at it, or if you just go on Google a motor driver, say an Arduino motor driver, you'd be able to see that that particular motor driver you Google, you find that there are some diodes sitting there. 4 of them, for the most part. If that motor driver is a 2-channel, you'll have 4 of them sitting there. The idea is that when it comes to stop, if you're driving this with maybe a 12 volts or 9 volts, if it comes to stop, probably you'll have maybe 2.8, 2 volts in residue. Okay, now you have to collect that and dissipate it, because if you leave it in the circuit will start overheating like that. So then you need those diodes to be able to do that. That's one way you can use diodes. The second way is we use diodes in what we call rectification, rectifier. Okay. Now, because these are short cohorts, some of these things will not be able to go in details with. Your job is now to go and research in detail the diode, to go and research in details about the rectifier and things like that. See, people who join late, yes, Donald. Yes, Donald, you can go ahead. You raised the hand.
Yes. Yeah, thank you very much. I was going to ask like how diodes differ from rectifiers, but since you've mentioned to say like we can actually do like a bit of research about it, so yeah, I think like I will conduct a research.
Before that question, I was just about to talk about the other application of diodes. So the other application of diode is rectifiers, as I said. Now, if you have diodes that you have arranged in a particular order, okay? If you have diodes that you have arranged in a particular order, you can now form what you call a rectifier. This rectifier can be either a half wave rectifier or it can be a full wave rectifier, depending with the way you have arranged your depending with the way you have arranged your diodes like that. So we are saying because the diode has the ability to block that voltage in that particular manner, we could actually be able to use a diode as a rectifier, because then what this means is that it will only going to allow current to flow in a single direction like that. That's what it's going to happen. So it means if this was AC, now let's change this to maybe, let's say, 125 volts AC, like that. If this was our load that would have connected here, what you're going to see is that AC looks like this. You'll have that, and that. That's a representation of AC in that particular manner. So this is your Y, this is your X plane. So this is the time, then this is your voltage in your Y. So if at this point you are getting 125 volts AC, and then that's a time or phase angle, in other words, what you're going to realize is that when this goes up like that, this is a positive side, then this will be the negative side. It means that the current will flow this direction, but when it goes to negative, what that simply means is now the current is flowing from negative to positive. On top, the current is from positive to negative. Down, the current is from negative to positive, like that. Now, because a rectifier blocks the flow of that current into one direction, or it's a unidirectional device, what this will mean now is that for an alternating current such as AC, that this part will be cut off. We'll only be having this part. So if you are going to repeat this pattern, you find another one here. The third one down here again will be cut off. You find another one there. The third one here will be cut off. So eventually what you're going to see is some current appears there, no current, current appears there, no current, current appears there, no current. Now, if I do this, it means now I have current in one direction, which is basically DC. Now this DC, because it's on, off, then we can now introduce the inductors we discussed earlier. The purpose of this inductor will be storing. When this guy is off, this inductor gives on. When this guy is off, the inductor gives in. So you're going to pick a perfect size of the inductor after you calculate your values to put at this point such that whenever this goes off, the inductor provides that DC. When this goes off, the inductor provides that DC. Eventually, you find that you have formed a straight line. And from you just be seeing that, oh, now I have power all the time. But in actual sense, this has been cut off, on, off, and then you have the inductor. Now, after the inductor, you might want to introduce a capacitor, as we discussed earlier, such that that capacitor is just going to clean whatever ripples that might remain in this. And then you have got a pure DC that you can now use to charge your phone or power another device. So that's the basic meaning of a rectifier. You'd have rectified from AC to DC like that. Now that can be either in form of full wave rectifier if you're using maybe one diode. If you're using 4 diodes, you'll be able to form a full wave rectifier. A half wave rectifier could be formed just by a single diode, but with 4 diodes, you'll be able to form a full wave rectifier. So that's another application of diodes. Okay. If you are working with DC, your design of your electronic component, the power supply is directly DC, the conversion, the rectifier is external. You may not need to do this rectification, and most of the basic electronic circuit you want to be able to design in the beginning, you'd want to be able not to involve yourself with designing the rectifiers. You might want to just get something that's already converting that power to DC, and then you feed in. The more you learn, then you can now start saying, oh no, I want my circuit to be able to do everything. I want just to feed it AC, it will be able to convert this AC to DC, and then let it now operate on that particular DC point. So that's how you can be able to work with this. So these components are quite important. They're quite important. So you could be able to design basic circuits, but what you have covered today. So next week when we meet, I expect you to go through all these things, gather this information together with all the components that you have touched. Next week when we meet, we are going now to design a functional circuit based using these components that you have discussed. That circuit that we design will have a capacitor in it, will have an inductor in it, or should I say it will just be based on the things that you have discussed. So we are going to have a functional circuit that you can actually, if you have a good idea, you can even produce a product on the market that you can be able to sell, but based on just these components that you have discussed. That's what you are going to do. So your job is to go and read a little bit about this, what you have the knowledge. As you come to that class next week, we'll be designing a circuit. The other week, you'll be converting that circuit into a PCB. Then the other week, we'll be now getting that PCB and converting into a tangible electronic product that we can manufacture. Then we would have said we would have achieved something. That should have been maybe in the 5th or 6th week. If this is our 3rd week. So that will be somewhere in the 6th week. We should be able to now say, okay, now we are printing the circuit that we designed as a group, and then we can now be able to showcase. Now probably we'll be able to ask those ones who have been consistently attending to come to the office and showcase the circuit that we designed together to the people to say, this is what we designed in the course that I attended for designing electronics. And we are moving that fast because the assumption is that most of the people that are here are somewhat people who finished either grade 12 or someone who has actually even went to college. So you are able to understand basics. We are not, trying to work with people who has not probably finished grade 12, no. So that's the idea. Is there a question? Is there a question? Is there a question? You can just go ahead and speak if there's a question. I'm saying you can go ahead and speak if there's a question.
Yes, maybe just out of curiosity, with regards to diodes, like since you mentioned to say they can, like when diodes are put in place, or should I say like when they're in a circuit, like they sort of like drop down like the flow of voltage. So like, would it be okay to use diodes like based on that purpose? As in like with the intentions of like trying to lower the flow of voltage like at a particular point in a circuit?
Yes, it's okay. A diode can be used as a basic voltage dropper. You can use a diode to drop the voltage, but it's not a precise solution. I have seen even professional work, professional product that you guys even buy from the shops where they have used a diode to drop the voltage. The advantage if you use a diode to drop the voltage is that the circuit will not be a bit efficient. The key word there is a bit. It will be a bit efficient because naturally, if all you want to drop, say you are working with a processor, then that processor operates at 3.3 volts. Such an example of a processor is a processor, actually most common microcontrollers operates at 3.3 volts, okay? An example of that is an Arduino microcontroller. The microcontroller, the Atmega 32 that sits on that Arduino board, the actual microcontroller by Atmega that sits on that board runs at 3.3 volts. There's another microcontroller called Novotron. It runs on 3.3 volts. There's another microcontroller such as an ESP32, runs on 3.3 volts, and ESP8266, 3.3 volts, ESP 3.3 volts. So if your voltage, the available voltage that you have is 4 volts, putting a diode in between to drop that 4 volts to 3.3 volts using a diode is a perfect solution. However, it is not a precise voltage regulator because the voltage drop is not perfectly constant and varies slightly with current and temperature. So if your temperature varies, the voltage will vary. If the current varies, your voltage will vary. For a certain application where you precisely want voltage control, a perfect diode that you would want to use is a diode we call a Zener diode, okay? Or basically just using a voltage regulator such as a linear dropout voltage regulator. But in a situation where all you want is just to drop the 0.7 volts and that particular device that you want to power is not sensitive to a voltage fluctuation, yes, you can use a you can use a diode as a voltage divide, as a voltage dropper. Yes. Is there another question?
There's no question. There's no question.
All right. Is there a question? I was saying, is there a question?
Yes, there is a question.
Hey, go ahead and ask.
Yeah. So my question is that one of the application of a diode is in current isolation. Now my question is that in an instance, I have two DC sources, e.g. a battery and a solar. So how can I use a diode in this situation to isolate the current of these two sources?
So when you say current isolation, you mean that there's no direct connection between the two sources that you are working with? Is that what you're implying by that?
Yeah, so what I imply by that is whereby you have got two sources, we have DC and the solar, then a diode is sitting in between, and then it is then to allow one current to come in at a time, like isolating the current.
Mm-hmm.
Yeah, so that's my question. Now, how can you use a diode? Like, how can you make a setup, a proper setup to manage this situation?
Okay. So when you are using a diode and isolator, you're not using a single diode. Okay? But actually using that diode basically as a bypass. The correct word might be bypass diode. So, example of a solar module. A solar module, solar panel. Can you mute your mic? There's a lot of noise coming from here. So, if I give you an example of a solar module, let me just go a little bit up here. So, a solar panel is made like this. So this is a main frame outside, which you guys call a solar panel or a solar module. Then inside, there are cells, solar cells. So this is a cell, this is another cell, okay? And this is another cell. That's another cell. And these cells can be as many as they can, depending on the design. This is a representation. We don't go and look out for a solar that has 2 cells like that. Now, these cells are getting sunlight and converting it to electricity. How then do you collect that electricity so that it is usable? You can find, for instance, that this particular cell is just giving you 0.5 volts. That's what it's giving you. So you want to connect this cell in series with that cell. This connection here is called a finger. So this line and this cell and that cell is connected by a finger. Then that will be connected there with another finger, that with another finger, like that. 0.5 volts, 0.5 volts, 0.5 volts. Now, similarly, this side, that will still be the same thing. Then we know that voltage in series is a multiple. So at the end here, what do we have? We have 2 volts. Okay? At the end here, we have 2 volts. All right? So then, these 2 volts, we can now run what we call a bus bar there, and a bus bar here. Okay? So this can be tapped from that bus bar. This we can tap it from a bus bar like that. Pay attention. What's happening here now is that we have 2 volts, we have 2 volts. Okay? So the sum of these two is 4 volts. So we want to connect this line and this line in series. So the way we are going to connect that in series is just to make sure that this end connects to that end and then it continues like that. So we have 4 volts. So it means if this is our positive, this is our negative, across here, what you have collected is 4 volts. So this solar panel will be said it's a 4-volt solar panel. Now we have connected this string of cells and this string of cells in parallel to each other. Why? We want to multiply current because current in parallel is multiplied. So we have again achieved that. Now the problem here is this. If you install this solar panel at your house or in your laboratory, or wherever you are working, and for some reason there's a shade on this particular solar panel, okay, whether you have put a cap, you haven't put it nicely, or if you have installed it on the house, the tree casts a shade on just one single cell. The resistance that will be in this single cell will be so high such that the total cumulative voltage up to this point might be so low, such as maybe you can even just get a 0.5 volts at the end instead of a 2 volts. Now you say, as an engineer who is designing this solar panel, we are going to say no. So what I want to do is, even if that there's a problem with this, I want to be able to bypass so that this doesn't affect. So I'm going to bring here that, and I'm going to put a diode. That. This is the isolation we are talking about. I just wanted to come from afar so that you can view the picture. So from here, you can quickly think to say, oh, so this is how all solar panels are made. Yes, yes, that's how all of them are made. Okay, unless that solar panel was made by an engineer from a Kantemba University. But if you're a proper engineer, this is how you're going to design the solar panel. And all the solar panels that you see on the market, they are like this. Okay. Now this, I'm just showing you a basic example. Now, what have I done here? What I've done here is this. If, say, there's a shade here, or the worst case that this is broken, there's a crack here or anything like that. Now, the flow of current is coming here or like that, or the whatever, the flow of the signal, the voltage, whatever that's happening there. When it reaches here, what do you think is going to happen here? Jonas, what do you think is going to happen? Quickly give the response. What do you think is going to happen? Jonas.
Hello.
What is going to happen there?
I've got a network problem here, so yeah, so I can't see what is happening there. I'll stop seeing.
Ah, okay.
But
That's
I was following.
mm.
I've answered my question.
Okay. So what will happen for it's unfortunate that you're not seeing. For those who are seeing, what's happening here is that when this hits here, this is going to provide a high resistance. Okay, electricity would choose a path with the least resistance. So it will realize that, oh, this was offering 10 ohm resistance as an example. But then I've got another path here that is offering 2 ohm resistance. So it will choose to go through this particular path and then rejoins back and the journey continues like that. Okay. So by doing this, and obviously there's another bypass here that would be like that. Okay. So by doing this, it means that we have navigated the cost of losing, the flow of that power here by means of this bypass diode. So that's what diode isolation is all about, like that. That's how it works. That is your question. It's unfortunate you haven't seen, because I labored to draw a lot. Yeah. All right.
Yeah, the screen is I don't know what other thing to the screen, but I couldn't be able to see.
Go back.
Okay.
When you watch
Thank you.
on YouTube, I think it will be more.
Yeah, I'll follow. Thank you so much.
All right. Cheers, guys. See you next.